This video is about electrochemical electrodes. It corresponds to sections 38.2 through 38.5 of Applied Analog Electronics. The basic notion of an electrode, as discussed previously, is that it's a place where electrons can leave a wire or enter a wire. And because we're talking about electrochemical things, we're talking about an electrolyte around the wire. So we've got electrons leaving or entering a wire into an electrolyte. That notion of an electrode really only applies to one sort of electrode. So let's take a look at the two sorts of electrodes that we've got. The first sort is one where we have a wire and then some perhaps surface treatment on the electrode, and we surround that with an electrolyte. And what happens in this sort of electrode is that electrons either leave the wire, resulting in some chemical reaction happening on the surface here, and negative ions going into the electrolyte, or positive ions coming out of the electrolyte, or electrons going the other way, electrons coming out of the wire, and that means that either negative ions are coming out of the electrolyte, doing some reaction on the surface of the wire, or positive ions going into the electrolyte. So you've got electrons going one way or the other, and some surface reaction happening between the electrode and the electrolyte. Those sorts of electrodes, which correspond to the standard notion of electrode of a place where electrons enter or leave a wire, is called a non-polarizable electrode. And we have a good example of that we'll be looking at in the lab. If you make the wire out of silver and you put some silver chloride on the surface of the wire, then we have a pair of reactions. One of them is just that the AgCl can break apart into Ag and Cl, separate ions. And this is basically silver chloride dissolving. And silver chloride does not dissolve all that well, so this reaction under normal situations where you just have the electrode sitting in an electrolyte, basically it's in an equilibrium and very little happens. There's another reaction, which is that Ag plus an electron can turn into just silver. Now we can put these two reactions together, and what we have is AgCl plus an electron going to silver plus a chloride ion. Now this reaction is one that we can drive from the wire by, if we put electrons through the wire here, have a current, then the silver chloride that's on the surface of the electrode turns into silver on the surface of the electrode, and chloride ions go into the electrolyte. Or if we take electrons out of the wire, we drive this thing in the other direction. Chloride ions come out of the electrolyte, reacting with the silver to make silver chloride and releasing the electrons to go up the wire. So this sort of non-polarizable electrode, basically you need to have a voltage between the electrolyte and the wire in order to drive this current, and you can model the whole thing to first approximation as a resistor. And the resistance depends on things like the concentration of the electrolyte, the amount of silver chloride on the surface of the wire, the area of the wire, all sorts of constraints there on how the thing behaves. But first approximation, it's just a resistor. All right, let's take a look, however, at another type of electrode, one that we'll also look at in the lab. And in this one, we again have a wire, And we again have electrolyte around it. But the difference is we've now got an insulator. Separating the wire from the electrolyte. What this does is it means we don't have direct electrochemical reactions happening at the surface of the wire. A good example of this is if we have stainless steel. What is stainless steel? It's basically any steel that has at least 10% chromium in it. And why is it stainless? Because when we try to oxidize this steel, instead of getting rust, iron oxides of various sorts, what we get is chromium oxide. The chromium oxide binds tightly to the steel and is not soluble. It doesn't flake off the way iron oxides do, the way rust does. And so the chromium oxide sits there on the surface and blocks the electrolyte, the water, the oxygen, whatever it is that's out there in the outside the wire, blocks it from getting to the wire so that the wire now does not corrode. Of course, for stainless steels to work, they have to be in an oxidizing environment so that the chromium oxide forms. If you put stainless steel in a reducing environment, the chromium oxide can be reduced. You end up with the chromium, and the iron can be exposed for reactions with various things in the electrolyte. So you generally want to use stainless steel only in mildly oxidizing conditions. We haven't got chemical reactions happening here. How then is this an electrode? Well, if we change the potential on this wire, we end up with an electric field here at the surface of the insulator, and we can get some movement of the ions within the electrolyte. So we can get alternating current to flow. In fact, if you think about this, it's a pretty easy model. We've got the stainless steel electrode that conducts. We have got the electrolyte, which conducts ionic currents. And in between, we have the chromium oxide insulator. So this is just modeled as a capacitor. So this is what's called a polarizable electrode, because you can put a potential across the capacitor and polarize it, which means basically charging a capacitor. Now, if things were ideal, we'd be done. We'd say we have non-polarizable electrodes, we've got polarizable electrodes, resistors and capacitors, great, we're done. Except for the real world's never that nice. What we end up with is things that have some sort of insulating characteristics on the surface. They're not purely the silver chloride ideal, gee, everything conducts, nor are they the pure, gee, there's an insulator here that's perfect, no current gets through it at all. And so what people usually do when they're modeling electrodes is to take an approach that sort of looks at having both properties here. So we have a resistor, which would be what we would all we would expect if we had a non-polarizable electrode. We put that in series with a capacitor, which is what we would expect if we had a polarizable electrode, but the polarizable part has a resistance in parallel with it, which is basically leakage through the insulator. So if we had something that was a perfect non-polarizable thing, this capacitance here would basically disappear and we just have those two resistors in series, we'd have a resistor. If we had a perfect polarizable one, this resistance would be infinite, and this resistance would be 0, and we'd have just a capacitor. In practice, this model is a very popular one for people doing bioelectronics because it captures stuff that's in between. It's useful to take a look at what sort of Bode plot we would have if we looked at impedance as a function of frequency. So we've got Z on a log scale here, frequency on a log scale here. What we would expect to see? Well, at extremely low frequencies, way down close to DC, this capacitor is going to be an open circuit. So we're going to see something here. Let's give these two resistors names, R1 and R2. We would have R1 plus R2 at very low frequencies. What would happen at very high frequencies? Well, at very high frequencies, the capacitor is basically a short circuit, and we would expect to see something that's basically just R1. So I should say this is the magnitude of the impedance. We're not looking at the complex part here. And what happens in between? Well, we're going to get something that slopes down here, and this sloping line here is going to be essentially where the capacitor is affecting the impedance. So you can look at corner frequencies here and here based on what these resistors are. That model is a very popular one, as I said, in bioelectronics. When we measure things, though, we don't often see that. What we often see is something that does the right thing here sort of at the ends, but has a much gentler slope than a capacitor should have. And we can do the same sort of modeling for this that we did for the inductors, or the inductor-like component we used in loudspeakers, by modeling this capacitor. Instead of being 1 over j omega c, we can do j omega times 1 second to the alpha times m. I mean, that's exactly the same component we used for the inductor-like components. We can do that for capacitor-like components, but alpha now less than 0, so it's coming out on the bottom. And m here is again going to be in ohms because we've made, by putting the 1 second here times omega, we've made that unitless. So we can model things that look like electrodes pretty reasonably with 3 components, one of which is the 2-parameter capacitor-like nonlinear impedance. Now, when you're doing modeling, though, you may not see this entire curve. For instance, I said this R1 plus R2 occurs at very low frequencies. You may not measure at that lower frequency because this may be down in the, takes days to get this. So if you only see part of a curve, like just this higher frequency part here, there's no way to estimate what R2 is. And so you might as well just say, pretend it's infinite, and just model R1 and C. Or R1 and this capacitor-like component. So don't try to include in your model things for which you can't estimate the parameters. Similarly, if this R1 only occurs at very high frequencies and you don't see it, you only see a dropping line, well then you can't estimate R1. You might as well assume it's 0. And then you would end up with just R2 and C or capacitor-like thing. Similarly, if you just see a constant horizontal line across your entire frequency range, just model it as a resistor. You haven't got any capacitor-like behavior. You don't need to model capacitor-like behavior if it isn't there. So when you're modeling an electrode, first figure out what the electrode's doing, measure it, and then determine what's the appropriate model for what you've measured. And it'll depend on what frequency range you're interested in. If it's constant over the frequency range you're interested in, it's a resistor. If it's sloping down at impedance inversely proportional to F, it's a capacitor. If it starts sloping down but not at 1 over F, then you can use this capacitor-like model to capture its behavior. If it slopes like that and then goes flat, then you might want to put a resistor in series. If it starts out flat and then slopes down, you might want to put a resistor in parallel. So if you've got the entire behavior with a flat spot, a slope, flat spot, then two resistors and a capacitor or capacitor-like nonlinear inductor and impedance. So there's a lot of different models all encapsulated in that one schematic, because you should leave out those components whose values can't be estimated. And that's basically it for what you need to do with electrodes.